Welcome to the final video in this series of short videos on the theory of electrolytes. In the previous videos, linked in the description below, we have been emphasizing essentially acids and bases. To recap, electrolytes are solutions that conduct charge. In order to conduct charge, that means the solute has to be ionic. They fall into two categories. They can be strong, meaning that they dissolve completely in water. And we've seen previously that there are 6 strong acids: hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, and sulfuric. And there are 7 strong bases: lithium hydroxide, sodium, potassium, rubidium, and cesium hydroxide, the group 1 hydroxides, plus strontium and barium hydroxide from group 2. Electrolytes can also be weak, meaning they exist in equilibrium in water. However, all the discussions about acids and bases, however, ignore one simple fact. They don't constitute all of the electrolytes that are possible. In addition to acids and bases, salts also act as electrolytes, and they can also be either weak or strong. At some point or other, you've probably learned, and most people understand, that salts come in 2 varieties. Looking at the common anions of nitrates, chlorides, sulfates, sulfides, hydroxides, and carbonates, people generally classify salts as either being soluble or insoluble. For example, all nitrates will dissolve in water. You've learned chlorides dissolve in water, with the exception of silver, lead 2+, and the mercuric ion. Sulfates generally dissolve in water, except for strontium, barium, and lead ions. Sulfides generally do not dissolve in water, except for the group 1 and group 2 sulfides and the ammonium sulfide. Oxides are insoluble in water, except for, as shown, the strong bases, the group 1 hydroxides, strontium and barium, and again ammonium. Carbonates are almost exclusively insoluble, except for lithium and ammonium again. So under this way of looking at things, you basically have 3 common anions that generally make soluble salts, and 3 very common ions that generally make insoluble salts. While this is easy to remember, it is essentially incorrect. The soluble salts do dissolve completely in water. However, the salts that are counted as insoluble are actually weak electrolytes, and they exist in equilibrium. Looking at the salt that's generally considered to be insoluble, lead chloride, we see it actually is a weak electrolyte and exists in equilibrium with lead 2+ and 2 chloride ions. Since it is in equilibrium, it will be defined by an equilibrium constant, products over reactants. That equilibrium constant for salts is called the solubility product. And it's equal to the products, Pb2+ times a chloride ion. As there are 2 chloride ions, that's squared. A major difference in the solubility product comes from the fact that if you're talking about salts, the reactant is always going to be a solid. Therefore, the denominator in the solubility product is always essentially 1. So KSP looks different than other equilibrium constants, but in reality, it's not. What the solubility product represents is actually the solubility product is actually a measure of the maximum solubility of a salt. For example, with lead chloride, the concentration of lead 2 plus and chloride minus squared is equal to 7.1 times 10 to the minus ninth. So, if one is in pure water, again, using the regular equilibrium of setting up a table where you have all of the reagents on top and the initial change and final concentrations on the sides, you will start with X amount of lead chloride. If I have maximum solubility, I will get X amount of lead 2 plus and 2X amount of Cl minus for every 1 PbCl2. Plugging that into the solubility equation, you have 7.1 times 10 to the minus ninth is going to be equal to X amount of Pb2 plus Cl squared, which is going to be equal to X amount of lead plus 2X squared amount of chloride ion, or 4X cubed. So, in absolutely pure water, the solubility of this salt would be 1.2 times 10 to the minus third molar. However, there are limits on solubility. Water is very rarely pure. This can show up in several ways. The simplest one is called the common ion effect. Again, this is best demonstrated by an example. If I had lead chloride in a 0.1 molar sodium chloride solution, you will notice that the solution already contains chloride ions. You deal with this the same way as any other equilibrium. Your equilibrium remains the same. Lead chloride is in equilibrium with Pb2 plus and 2 Cl minuses. The solubility product also remains the same. It's a concentration of lead ion, chloride ion squared, 7 times 10 to the minus ninth. What changes are your parameters in the equilibrium table. You still have these same reactants, and you are still looking for the initial, the change, and the final. However, in this case, I'm adding an unknown amount of lead to a solution that already contains 0.1 molar chloride. So, at the end of the day, my solubility product of 7.1 times 10 to the minus ninth is going to be equal to the amount of lead I have plus the chloride, which I started with 0.1 molar, and now I am adding 2X. One can make an assumption in this case. X is going to be a very small number in order for the result to be 10 to the minus ninth. So one can assume that 0.1 plus 2x is going to be roughly equal to 0.1. So as a first estimate, you get the solubility product, 7.1 times 10 to the minus ninth, is equal to 0.01 times the maximum solubility x. This gives a tentative answer of a solubility, in this case, of 7.1 times 10 to the minus 7th. But again, if one is making an assumption, one has to check, and one checks by throwing the assumption back into the original equation. If we substitute 7 times 10 to the minus 7th for x, one winds up with 0% error of an answer of 7.1 times 10 to the minus 9th, which means your assumption was correct, and it also shows from 10 to the minus 3rd to 10 to the minus 7th, the presence of a common ion severely restricts solubility. A second way that the solubility of a salt can be limited is by trying to dissolve the salt in a salt solution or in salt water. If you have an electrolyte solution, you're essentially going to be experiencing what is called non-ideal behavior. Put simply, salt water will behave differently than fresh water will, and the question is, how much? The how much is determined by using the activity of the ions instead of the concentration. Activity is related to concentration, where A, the activity of ion X, is equal to the concentration of that ion, times a term called gamma. Gamma is called an activity coefficient. It's essentially a fudge factor. If a solution is behaving ideally, gamma will be 1. If it deviates, gamma is always less than 1 and is an indication of what percentage of expected behavior you're getting. This is further complicated in a salt solution. If you have an electrolyte, the effect of the positive and negative ions cannot be separated. If you go to a grocery store, you can't buy a box of sodium plus and a box of chloride minus and make your own salt. Therefore, what you get is a composite of the activity coefficient. As shown, the base 10 log of this gamma plus minus is equal to several terms. Gamma plus minus is the average ionic activity for all the ions in solution. The terms Z plus and Z minus are the oxidation states of the cation and anion of the salt that you're trying to add to the solution. A is a solvent-specific constant, which happens to be 0.509 for water. And the last term, I, is an indication of the ion strength of the solution. This seems complicated, but the math is actually rather simple. The ionic strength is equal to 1/2 of the sum of the concentration of each ion times the oxidation state, or the charge on that ion, squared. Once again, this can be seen by an example. We'll keep the same lead chloride solution, except this time we'll try to dissolve it in salt water, where the solution is already 0.05 molar in sodium sulfate and 0.075 molar in copper 2 bromide. Once again, I'm interested in the same equilibrium. Lead 2 chloride in equilibrium with lead 2 plus and 2 chloride ions. The value of the solubility product does not change, 7.1 times 10 to the minus 9th, except now it's equal to the activity of the lead 2 plus times the activity of the chloride ion squared. Or put another way, the activity coefficient gamma plus minus times the lead concentration, and the activity coefficient plus minus times the chloride ion concentration squared. Breaking down how to determine gamma plus minus, you have, for starters, we're trying to dissolve lead 2 chloride. So in the term for the log of gamma plus minus, Z plus would be plus 2, the charge on the lead ion. Z minus would be minus 1, the charge on the chloride ion. And since we're in water, A would be 0.509. Your ion strength would again be 1/2 of the concentration of each ion times the charge of that ion. So I'm starting with sodium sulfate. I have a 0.05 molar sodium sulfate solution, which means the concentration of the sodium ion would be double. If it's 0.05 molar Na2SO4, that would be 2 times 0.05 for the concentration of sodium. The charge on sodium is plus 1. One sulfate ion would be at 0.05 molar, and a sulfate is minus 2 squared. I have my copper 2 at 0.075 molar with a plus 2 squared. And once again, for each copper, I have 2 bromide ions, so the concentration would be 2 times the 0.075 times the charge on the group 7 bromide minus 1 squared. This gives a log of gamma plus minus equal to 1/2 of 0.75 or 0.375, which means gamma plus minus itself is a negative 0.6234. Giving 10 to that gives the activity coefficient of 0.238. So to get my solubility, I know the concentration, I know the value of the equilibrium constant is 7.1 times 10 to the minus 9th. I also know, as usual, without showing the table, if I'm trying to dissolve X amount of lead chloride, I will get X concentration of Pb2 plus and 2X concentration of Cl minus. Each one of those multiplied by the activity coefficient 0.238 now gives 0.0135 times 4x cubed. So once again, the concentration in solution is reduced by the presence of salt, and I get a concentration of 5.1 times 10 to the minus 3 molar. Again, less than it would be in pure water. This is used in reactivities. If you have a soluble product, you can retrieve it by simply adding more salt to the solution in a process called salting out, because solutions are less soluble in salt water than they are in fresh water. A third and final limit on solubility is mixing two solutions together. For example, if I add 0.053 grams of magnesium bromide to 100 milliliter solution with a pH of 10.4, will magnesium hydroxide with a solubility product of 1.8 times 10 to the minus 11 precipitate, or will both salts remain in solution? To answer this question, we go back to the fact that for all weak electrolytes, you are dealing with equilibrium, which means in addition to K, there is something called a reaction quotient, Q. Q is also equal to products over reactants as related by the balanced equation. However, I can have any ratio of product of reactants, only one of them will be at equilibrium. So you have a situation where you have two numbers, Q and K. Q can be greater than K, which would indicate you would get a precipitate in this case. If Q is less than K, I have fewer reactants, so there will be no precipitate. Or if I am at equilibrium when Q is equal to K, it means I have a saturated solution. So to calculate Q, I go to the reaction that I'm interested in. The question asks about magnesium hydroxide. That is going to be in equilibrium with Mg2 plus and 2 OH minuses, which means Q, similar to KSP, would be equal to the concentration of Mg2 plus and the concentration of OH minus squared. So, I have 0.053 grams of magnesium bromide at 184 grams per mole in 0.01 liters of water, means that I would have a 2.88 times 10 to the minus third molar Mg2 plus concentration. Using the knowledge of acids and bases, I am given a pH of 10.4. pH is the negative log of H plus, but in this case I have a base. So I would need the pOH, which would be 14 minus 10.4, or a pOH of 3.6, meaning I have a hydroxide concentration of 2.5 times 10 to the minus 4. Plugging these into Q, I get an answer of 1.82 times 10 to the minus 10th. This is close, but I'm still a factor of 10 above the value of KSP. So the answer is Q is greater than K, and a precipitate will occur. This concludes the discussion of electrolytes in general. Strong or weak, soluble in water or in existing equilibrium, where electrolytes could be acids, bases, or as this video shows, salts. Thank you very much for listening, and I hope you found this description useful.